In problem 2.3, we are asked to show that there are no acceptable solutions to the time-independent Schrödinger equation for the infinite square well with energy equals 0 or energy less than 0. So let's start by sort of writing down the time-independent Schrödinger equation that we've been using all this time, which says that negative h bar squared over 2m times the second derivative of psi with respect to x, specifically little psi, plus our potential v of x is equal to the energy E times psi. And we're specifically working with an infinite square well, remember, and for an infinite square well, v is just 0 inside of our well, so for all intents and purposes, we can just get rid of it without any consequence. And now we have two cases where we want to show that for both of these cases, using these values for e gives us incorrect expressions that cannot be solved. So let's start with the first one, which is e is equivalent to 0. And if we were to solve this, or if we were to just plug this in, we just get the same expression on the top as before, and this is now equal to 0. And since this is equal to 0, we can instantly sort of cancel out these constants that are being multiplied at the front, and now we just have the expression that the second derivative of psi with respect to x squared equals 0. And this is obviously a very sort of trivial solution, or this is a very trivial expression to simplify or to solve, and we get that psi is therefore equal to some constant a times x plus some constant b. And now, this is obviously a valid solution, but now we have to show that this is not reconcilable with sort of the boundary conditions for our infinite square well. So, let's first consider what our boundary conditions actually are. Well, back in 2.2, early on, one of the things we said was that psi has to sort of be continuous. So because of that, we necessarily require psi of 0 and psi of a to be equal to 0, because these are the edges of our well, and since psi equals 0 outside of the well, they must equal 0 at this boundary as well. So let's plug this in. So psi of 0 is just equal to b, and this must equal 0, so therefore b must necessarily equal 0. Therefore, our new psi expression is just a times x. Well, now if I plug in my second condition, psi of a also has to equal 0. Well, psi of a equals big A times a, and since little a here is non-zero, this must necessarily mean that a must also equal 0. So therefore, our solution is now just psi equals 0. And this is obviously a trivial solution. It doesn't actually, it just represents the absence of a particle. So therefore, it is not possible to describe a particle inside of a square well with an energy of 0. We'll get to the implications of this later on, but for now, let's move on to the second part, which is the case where the energy is less than 0. Hopefully, we get something for this. Obviously, we won't, but let's just see how it doesn't work. So if energy is less than 0, well, we have the same sort of expression here that we have before. But now, since energy is no longer 0, we can actually create an exponential expression for this. So let's do that. So d2 psi with respect to x squared is now going to be equal, where I move everything out to the other side, negative 2m times e over h bar squared times this times psi itself, and this is obviously just an exponential function. We can simplify this very easily and get psi equals some constant at the front, which let's, well, actually in this case, not even a constant at the front. Let's call this e to the power of the square root of negative 2me over h bar squared. And then we add the x at the front like this. And this is being added with some other arbitrary function. So plus, let's say, ax plus b. So well, actually, no, I'm sorry. This is not even, that's not right at all. That is not something you're supposed to do for exponential functions. My apologies. It was a mistake on my part, but this is our final solution. And from here, we can do a bit of simpling. First off, there's a negative in this expression, so we can move that out. So psi is going to be equal to e to the power of I, and then times the square root of this entire thing in the inside, times x. Where x is outside of our square root. And from here, we know that e is less than 0, so we can sort of do this again, and this gives us psi is equal to e to the power of negative square root of 2m, and this time we're going to replace e with some constant c over h bar squared times x, where we can just say that c is some value that's greater than 0 now. And at this point, we have solved this expression, and we will once again sort of convey, or we will once again apply our boundary conditions. So first off, we require necessarily that psi of 0 must equal 0, and instantly, hopefully you see that this is not true, or not possible, because psi of 0 is equal to e to the power of 0, which is equal to 1, which is obviously not equal to 0, so therefore this is also not valid. And because of that, we also conclude that e cannot be negative. So what we've concluded is basically that for a particle sort of in our infinite square well, the energy must be positive. And this sort of goes against classical mechanics, because in classical mechanics, we are allowed to have an object just sit there and have 0 energy. If I put a ball and I just put it on the ground at rest, then it has 0 energy. It has no kinetic energy, it has no potential energy. However, evidently in quantum mechanics, apparently for certain systems, there's actually some minimum energy that the system needs to have if we want to actually describe it with a particle inside. If there was no particle in my square well, then I would just get an energy of 0, which is exactly what I derived here. Psi equals 0 inside our well, representing having no particle whatsoever. In this case, we have an energy equals 0, but this is obviously not interesting at all, because now we're just looking at a system with nothing inside. The moment we introduce a particle, even if that particle apparently is at rest, in quantum mechanics there's apparently a minimum positive energy that something must have. And we can actually define what that minimum positive energy is, because we've already sort of solved for the energy earlier on when we derived the expression for the infinite potential well. We derived that the energy levels have to be equal to n squared times pi squared times h bar squared over 2ma squared. So evidently, the minimum energy here is going to be equal to when n is 1. So the minimum energy, which let's call E min, or EM, is going to be equal to pi squared h bar squared over 2ma squared. This is the smallest possible energy that our system with a particle in a square well can have. It cannot go lower than this. It must be this or higher. And evidently, since n is squared, we can not ever have negatives either. If n is negative 1, it gets squared to positive 1. If it's negative 2, it gets squared to positive 4. So as sort of a result of this, our derived expression for the energy that we obtained earlier on sort of directly supports this idea that E cannot be 0 or negative.